Hello, my name is Pengchen Yao, a PhD candidate from Huazhong University of Science and Technology. It's my honor to be here to share our recent work, and in this talk, I will present Grammar, a locality-aware energy-efficient accelerator for graph mining applications. Graph is an ubiquitous data type in our lives, like World Wide Web, social network, road network, and bioinformatics. However, performing graph analytics is extremely inefficient for traditional architectures like CPU and GPU. The reason lies in the sparsity of the graph data. As shown in the left figure, the data flow of graph analytics is significantly randomized. Therefore, as shown in the right picture, it will lead to significant memory overheads on general-purpose architecture due to the random memory accesses. So to cope with the problem, a lot of research has been proposed to build dedicated accelerator. With architecture specialization, hardware accelerators achieve considerable performance and become one of the most promising methods for graph analytics. However, all these accelerators are dedicated for graph processing and thus cannot deal with another important class of graph analytics. In general, graph analytics can be divided into two categories, including graph processing and graph mining. Graph processing computes vertex or edge property like BFS and PageRank widely adopted to analyze relationships. These applications generally adopt the gather-apply-scatter model, where each vertex interactively updates itself based on the property of its neighbors. Another aspect of graph analytics is graph mining. Graph mining applications search interesting subgraphs like subgraph matching and multiple counting widely used in finance and bioinformatics. They generally use extent filter process model, which is significantly different from GAS model. In graph mining, each subgraph interactively extends itself by adding one vertex or one edge to generate new subgraphs. Because of the differences in two process model of graph processing and graph mining, their memory accesses experience different properties. As shown in the left figure, graph processing mainly performs random vertex access. However, graph mining performs both random vertex and edge access. First, when we extend the subgraph, we need to read all edges of its vertices. Since the IDs of these vertices are discontinuous, every access in the first edge of a vertex is random. In addition, when we find a vertex to extend, we need to randomly read all edges between the extended vertex and the embedding vertices. As shown in the right figure, both of vertex and edge access can result in significant overheads in graph mining. Unfortunately, all existing graph accelerators are specialized for graph processing, which only has random vertex access. Because the vertex data is always less than tens of megabytes, these accelerators store them on chip to improve the memory performance. However, this design can hardly be used in graph mining because the edge data can be easily larger than several gigabytes. It is unpractical to store all irregular edge and vertex data in an on-chip memory with limited capacity. So since we can now store all irregular data, an intuitive question is whether we can store only a small portion of data to achieve good performance. To answer this question, we did comprehensive analysis and found a special extension locality in graph mining. By extension locality, we mean that the power law distribution in natural graphs is amplified during the extension. Here is an example. The access frequency of vertex 8 is increased from 12% to 30% as the subgraph enlarges. The reason behind this locality is the power law distribution and the extension nature in graph mining. That is, the high-degree vertices always have higher chance to be extended. Therefore, most of the subgraph will include these vertices during the extension, which in turn increases their access frequency. Our experiments indicate that 5% graphical data can generate at most 95% memory accesses. In other words, if we can locate and store this 5% data on chip, at most 95% memory access can achieve ideal performance. Based on this insight, we propose Grammar, the first accelerator designed for graph mining applications. Our first contribution is a Locality-Aware on-chip memory, which enables accurate estimation of access frequency. And our another contribution is DFS-based processing units, which minimize off-chip memory, off-chip communications, and maximize computational parallelism. When implementing our insight in memory subsystem, the most important thing is to locate this frequently accessed data. A direct mechanism is to predict using the vertex degree. However, as shown in the left finger, the accuracy of this mechanism decreases sharply as the iteration increases. To make precise prediction, we make a formalization and find that the access frequency is determined by both the vertex degree and its key hope neighbor's degree. While this new mechanism is accurate, its overhead can be even larger than the execution time for some algorithm. Fortunately, we find that the access frequency is mainly determined by the degree of the vertex and its one-hop neighbors. The reason is that the high-degree vertices and their one-hop neighbors connect most of the vertices and edges in the input graph. So multi-hop neighbors either connect with them or contribute little to the access frequency of them. So based on this observation, we propose one-hop prediction to achieve trade-offs between accuracy and the overhead. More specifically, we set k to 1 in our formalization for all sides of embeddings. We can see from the right finger that the accuracy can be larger than 97% and the overhead can be less than 3% when the embedding size is larger than 2. So with the one-hop prediction, we propose a specialized on-chip memory hierarchy, which consists of high-property memory, a low-property memory, and a controller. The high-priority memory statically stores frequently accessed data and is implemented by scratchpad memory. The low-priority memory dynamically replaces the other data and is implemented by set associative cache. As for controller, it dispatches memory requests based on the address. So although the overhead of one-hop prediction is small enough comparing to the execution time, it is still time-consuming to be computed at runtime. So here, we motivate with a basic idea to use vertex ID to represent access frequency. That is, the lower ID a vertex has, the more frequently it is accessed. So based on this idea, we propose a graph reordering mechanism to reorder vertex IDs in ascending order of access frequency. With the mechanism, the memory address of each request represents the rank of its access frequency, so that the controller can easily dispatch a memory request by comparing the address with a predefined threshold. If a memory request is dispatched to the low priority memory and misses on-chip memory, we also design a new replacement policy based on the global and local access frequency. So with the above designs, Grammar can efficiently handle random accesses. So another important thing is how to efficiently implement the computation model of graph mining. Traditional graph accelerators use a BFS model, which interactively writes the intermediate data back to out-chip memory. However, graph mining generally suffers from combinatorial explosion in intermediate subgraphs. Even a median-sized graph can quickly generate trillion-scale subgraphs when the embedding size is larger than 4. So writing them back to the object memory can waste a lot of memory bandwidth. To deal with it, we adopt DFS model proposed in Fractal to avoid writing back embeddings. However, DFS is hard to parallelize due to substantial transverse states. Transferring these states through the pipeline, as the typical accelerator designs, can largely increase the hardware overhead. To this end, we propose a node-based pipeline to achieve massive parallelism. Our basic idea is similar to data flow scheduling. We store all transverse states in scheduler model to avoid transferring them through the pipeline and use a unique token to locate these states. In order to locate the transverse states, we virtually divide the pipelines into several time nodes, and each time node is shared by an initial embeddings and all intermediate embeddings extended from it. With this design, each embedding can use a unique node ID to find its transverse states. Moreover, we also compress these states to further reduce hardware overhead and the work stealing mechanism to increase parallelism. So at the end, to evaluate our work, we implement grammar in an FPGA running at 200 MHz, and we also choose Fractal and upstream and baseline, and run them at a high-end server with 128 DRAM and 1 TB SSD. 3 traditional graph mining applications, click finding, motive counting, and frequent subgraph mining are selected to be tested on 7 graph datasets. Comparing to Fractal, we can achieve at least 12 times speedups for small graphs, 4 times speedups for medium graphs, and 1.8 times speedups for large graphs. In addition, we can also achieve at least 9 times energy efficiency. Comparing to upstream, we can achieve at most 130 speedups and 600 energy efficiency. So thanks at the end, thanks a lot for listening. If you have any questions, you can email the following address.